our friend, I cannot pronounce your family name, but I know that Josef is your first name. Josef is not just a very strong technical person; he also has a very good love for psychology. So it's one of his long life term hobby to study psychology, and that's why he's going to be a kind of like a therapist for databases in distress. This is going to be kind of like a healing of the trauma of the databases, right? So please welcome Josef.
Yes. Oh, thank you very much. I am really glad to be here. This is really conference to remember. I like this environment, so I want to thanks for the opportunity to give the talk here. And I will be really talking about database in distress and, of course, people in distress around crashed database. I work for a German company, Credative, and we do support for open source products, and Postgres is one of our biggest topics. Here are a few information about me. I have like more than 30 years of experience with different databases. I worked for different companies and also for some very interesting startups. So I could work with very interesting environments and interesting technologies. I'm originally from Czechia, but now living 11 years in Berlin. First of all, there was already Simon Ricks mentioned in the first talk. I want to acknowledge that also I was inspired by his talk given in Prague, and he used these words. He said that we still need to ask stupid questions because we could be, satisfied that Postgres is number one, which means we are the best. And he said, this is not true. It just means that it's number one. And he says that new users are asking questions, and those are good questions. So we need to ask questions about everything. And this is why I embarked on this talk and on this research, because I wanted to understand corrupted databases in more technical details. But I must also acknowledge that there are already some amazing talks from previous conferences and some articles, and I built on them, because without these talks and these articles, my talk would be looking differently. So I strongly advise look at those talks, and you will find a lot of information there. I will just dissect now some things in more details to show you how is it working behind the scene. First thing is that Postgres is actually remarkably stable. If you run Postgres on Linux under typical circumstances, it is rock solid. Almost all of these databases I have to repair were on Windows, and yes, sorry about it, but it is as it is. And in one case, a badly crashed Kubernetes cluster damaged the data, so it was a situation on Linux, but created by Kubernetes. And what was important in these all cases, those companies did not have no useful backup, any useful backup. Problem is that some types of backups can mask corruption. I will talk about it. So we have these block checksums, which are available for check of data corruption, but in Postgres 17 and older, they were not enabled because of performance concerns. And without these with these checksums, many types of corruption remain undetected and are revealed only when you read those specific records. So this is why often those corruptions are shown when you try to do pgdump backups. Because a PG-based backup actually copies data as they are, the whole files, and it does not check data integrity. So you can have years of backups done by PG-based backup. They could be all corrupted, and you may not know it about it. So when you try pgdump, and it was the situation in all those cases when they try to do pgdump, and they have seen something from these errors. So first of them is invalid page in some block, which is like situation which is usually seen in this like most common. And second most common is this could not access status of transaction with some ridiculous number. I will explain how they actually happen. And if you have a damaged sequence, there could be problem to read data from that sequence. And in some rare cases, corrupted data can even crash the session. So you get memory segmentation fault, and that session crashed, and postmaster must restart all those backends because shared memory could be corrupted. Very often, that corruption is hidden in older, rarely accessed records, maybe in even frozen tuples, because they are not visited by AutoVacuum. But even if AutoVacuum fails on some corruptions, you may not notice it because you can have millions of records in log, and one of them is error from AutoVacuum. And this is what I was discussing with that guy who is actually developing pgweasel log analyzer. Sometimes one error in dozens of gigabytes of logs is more significant than millions of errors. And this is exactly this situation. So I said that pgdump can show what corrupted objects, but problem is that this will end on that first corrupted object which is found. So when we analyzed those corrupted databases, we used this script in PowerShell, which generally reads all databases, reads all relations from each database, and tries to dump each table separately into a specific file and logs those errors into logs. So if we later see those error logs which have some content, we see that these objects are damaged. This is like first sanity check you can do on your database to see how many really damaged objects you have in a database. And we have now pluggable access method for storage of data, but heap is still default, and all databases have been created using heap tables. So to understand what is happening, I created corruption simulator in Python, which surgically damages different parts of data block to give me precise behavior when some types of corruption happens. And this is what I will now show you. But first thing first, checksums. I already mentioned those checksums. We have them, we don't use them. Fortunately, in version 18, they now set checksums as default during initdb, which is a great step forward, and you will understand why in coming slides. This is that commit which actually did it, and there is also this ignore checksum failures parameter which controls that error handling. So how it looks like when you have database with checksums and some corrupted data. Here it is. Checksums are calculated for each data page, and they are stored as 2 bytes in the header. You will see it in other slides. And when Postgres reads data, it calculates checksums again and compares them with the stored value. And if there is some error, it will show that error which we already seen, invalid page in some block. That ignore checksums failure setting is default off. So by default, when there is some checksum error, that query will stop on first block which is corrupted, meaning which has different checksum calculated from checksum stored. But you can say ignore checksums failure on, and then it will report all those pages which are actually probably corrupted, but it can still exit on some other transaction. And this is usual situation. This could not access status of transaction of some huge number. We can easily cure those pages which have bad checksums using this zero damage pages setting. Default is off, and if default is off, then it will behave exactly the same way. It will end on first error. If you set it on, then it will not only skip those damaged pages, it will also zero them out, meaning we will lose content of those pages, but that content is lost anyway. I will demonstrate why. So if you have checksums, you do not need to be worried about any types of corruptions because it will be always shown as different checksum from what is stored. So I highly recommend if you will install new databases with Postgres 18 or even with 17, allow checksums, because especially if you run something in a very violent environment or on Windows, then it will help you definitely. But I also must mention that all those blocks which would be zeroing out, there will be lost. If you set those zero damage pages to off, again, it will not restore original content. But you must understand that it will zero out only those pages which were read during that query. So to zero out all damaged pages, you need to make sure that you read all data pages from that table. And after this, let's dissect data corruption on that low level of that data page. So, as I said, the heap access method is default, and here is the anatomy of data block, how we know it, how we love it or hate it. It's up to us. So there is this page header, which contains metadata for block management and integrity. Here are those item IDs. Here are tuples, and here could be special space, for example, in indexes. So when we add new record, item ID is added here as first after that header, and new tuple is added here at the end as first. So this way we go backwards, and that item ID stores position when that tuple starts and how long it is. So if we now corrupt some parts, we get a different behavior. If header is corrupted, then the whole page is lost. And without checksums, actually, Postgres can detect only corrupted header. And I will show that part of code. If those item IDs are corrupted, then we have no access to tuples. And if tuples are corrupted, then we will have ridiculous content in system columns and also in normal columns. So let's look at it, how it looks like. This is header. It occupies first 24 bytes of every page. It has these important values, and we can detect without checksums only like obviously damaged values. This is this part in code. I looked on release 17 stable and release 18 stable. Here you can see files and names of those procedures. And pay attention to this comment. Actually, there are many interesting comments in code directly, which say much more than documentation. So if you are looking for some problem, I highly recommend to go into source code. And what it says, following checks don't prove the header is correct, only that it looks sane enough to allow into the buffer pool. So without checksum, it's sort of guessing game. You know, we can only say if those flag bits contain valid values, if these parameters for offsets and block size fit into into numbers which we expect. So if it fits, we say, good, it is probably not corrupted. This is all we can say without checksums. We can say the data are probably sane. And here is explanation of those special bits. This is not that important, but let's look what we can actually analyze. We have several extensions, mainly pageinspect. At healthy header, you will get something like this. Important things here are those offsets and where that special part begins and page size. If that header is corrupted, meaning it was rejected by this test, then we cannot analyze anything. We always get this invalid page error. If we set 0 damaged page on, then page is zeroed out, and we will get only zeros. Everything is lost. Okay, this is corrupted header, but as I said, it's still like the best option from those corruption if we don't have checksums, because we can detect it. We have other types of corruptions which we cannot detect and which can even crash the session. So here is corrupted item ID array. These values saying us where tuple begins and how long it is. So if we take pageinspect function, heap page items, we can see how healthy page looks like. What is important here are those offsets and those lengths of those tuples. So first tuple begin almost at the end of the page, and every subsequent tuple is closer and closer to the beginning of the page. And here you can see different lengths of those tuples because there are some text contents, and therefore content is variable. This is healthy page, how we like it. We have here transactions which created those tuples. Here is CTID. Everything is perfect. What happens if we surgically damaged those item IDs? Yeah, this thing happens. You can see we have 8 kilobyte page, and we have offset 20 kilobytes. We have offset 17 kilobytes. And what we have here, length of that tuple, 28 kilobytes. This is how memory segmentation fault happen in the code. Because we can get two typical errors: invalid memory allocation request of some absolutely ridiculous size, or process was terminated by signal 11, and then you will see in Postgres log that there was memory segmentation error. This is how it happens. Because code tries to interpret these ridiculous values without checking for page size. And if we try to analyze it, yeah, I already showed version from pageinspect, but what about AM check? Yeah, well, unfortunately, AM check is not helping here exactly because these messages are quite cryptic. I spent some time thinking about what was the motivation to do this cryptic message, but problem is AM check is taking those ridiculous numbers seriously. It does not flag them. It does not say that it is impossible in page which has 8 kilobyte size, So this was corrupted item ID array, and now let's look at situation when we surgically damage only those tuples. So we have header intact, we have item IDs intact, and we damaged only that part with tuples. As we know, each tuple has its own header. And most important values are those transaction min, transaction max. There is also CTID stored, and there are some info masks. So if we look at healthy page, it looks this way. And here I used a page from Toast table because it has a very nice structure. Usual situation in those table is that data page has 4 records, each 2032 bytes long, and therefore everything is quite ordinary, everything is directly visible. So we have here 4 records in those table in this particular block, created by one transaction, CTID is perfect, everything nice. And when we damage it, what we get? We get this rock and roll. And this is where those strange errors, I cannot check status of transaction, where they originate. Because here are these ridiculous numbers, and we take them seriously. You can see also absolutely ridiculous numbers in CTID, and we also take them seriously. Because we somehow don't, think about situation that those ridiculous numbers could be product of data corruption. Because we say, okay, header is okay, we can read tuple, so what we find here is probably true. No, it isn't, because it's just damaged content. Because if you have damaged tuples, you have absolutely random content. Also, you can see those info masks are damaged and also these offsets. And here, Postgres actually crashes. And unless you do surgically deletion of those tuples, you cannot use that table. So let's look what we can do with this. Here is also when you select from that main table and only tuple table is damaged, you will see additional errors, which are all created by the fact that those table is damaged. Because it cannot find some chunks or unexpected chunk numbers and so on. And again, those are ridiculous numbers from corrupted tuples, and we take them seriously. So what to do with corrupted tuples? We have this nicely corrupted page. It's absolutely useless. It ends with that error that there is some transaction ID which we cannot check. So we can use PG surgery, and here is this heap force freeze, which will, as I said, freeze data. That function requires CTID, but you cannot use this broken CTID because it does not do sequential scan for CTID's values. You must actually estimate what is the right CTID on this page. So in this case, it's page 273, and we want to freeze first tuple. So let's look again on that first tuple. We have ridiculous xmin, xmarks, and also other values. What happens when we freeze it? Yeah, well, record is frozen. Transaction min is 2. CTID is what we expect, but all other values are still the same. And when we try to read that record, it returns either nothing or some gibberish. So freezing of tuples which are damaged this way is not feasible. We must simply kill them, and therefore we use this heap for skill, which again requires CTID, and when we kill it, that record is gone. And that way, we would need to kill all those other tuples. What would be really helpful here would be some function which would kill the whole data page, because here we have 4 tuples, but in some situation we can have like 200 rows in that page. So killing the whole page would be much more convenient. I tried AM check again, and here those messages are even more cryptic, because it actually presumes again that those values are okay, and tells me that there is some mismatch where tuple data begin, and it suggests that that tuple has, wow, 2,000 attributes. We have magical space in our database, 2,000 attributes. It wants to interpret those damaged data and gives these results without being ashamed, because those results are obviously nonsense. But yeah, this is as it is. So we must work with this. Only one page about corrupted sequence, because sequence is actually just non-transactional table with one data block and one row, and that row has those hidden system columns and 3 normal columns, and one of them is last value. So if that one data block in that sequence is damaged, you can either get this invalid page in block, or there are special errors in case of sequence, bad magic number in sequence. This is one of the most beloved error messages regarding data corruption. Bad magic number. Yeah, well, there are other magic numbers in corrupted data, but here we at least say. Yeah, and also this invalid memory allocation request happen here, and in some cases even that crash of that session. And when we try to select data from that sequence, it returns 0 rows. Okay, so I mentioned several times that memory segmentation fault. It is caught by postmaster. There are those functions which actually do it. And here is that part of code which then says that a process was terminated by signal 11. And this is it. There was some memory overflow, some segmentation fault in code. So what we really would need, some low-level sanity checks, at least, switchable on and off, because I can imagine that in normal situation, it could have like bad performance impact. But if you are repairing damaged database, you would give like gold for such checks, So can we cure corrupted data? Well, without valid backups, original data cannot be restored. And valid backup is not necessarily binary backup done by PG-based backup. You can have dozens of PG-based backup all corrupted and not know about it. If you use that, if you don't use checksums, which is actually normal in these days, only pages with invalid headers are detected. We can zero them out, but we still have other situations when corrupted data blocks contain unpredictable values, and therefore we need to either remove surgically those tuples or do salvage row by row, which can be very time consuming. How this salvaging good data row by row looks like. I think you understand that it depends on particular data model, how those tables are built. Here is just one idealistic example. When we have main table with ID as primary key, and there is toast table, and that toast table is damaged, then we still can select those values of primary key from that main table, and then try to select row by row based on that ID, and if it is okay, insert data into that new table, commit after each insertion, because there'll still be that segmentation fault error, and that way we can really go row by row, which is amazing when you have table with just 200 gigabytes and one damaged data block, which is situation we had by one customer. So you can imagine that it takes hours, dozens of hours. So this is one option. What about table which is so badly damaged that you cannot even select consistently primary keys? Yeah, well, we can select using CTIDs. This is the only way how we can try to select row by row. But here we must know how many pages in total are in that relation, and try to guess or find what is the maximum amount of tuples in data page. And then we can create dynamic query selecting using CTID really row by row, inserting those queries which are okay into that table where we salvage data. Again, it depends on a particular data model, so this is just some example. And we must commit after each insert, because that segmentation fault can happen quite often. And if it happens, we need to avoid these particular city IDs which actually cause that segmentation fault. As you can imagine, this is very time-consuming, labor-intensive, but for some clients, it was the savior. We spent like several days really restoring data which were damaged by some ransomware. Yeah. So these are like two examples how you can deal with it. And of course, what you need to remember, if you restore damaged data, then if data some are lost, then foreign keys might be compromised or most likely will be. So you either need to remove those orphaned rows from child tables or create some dummy rows in parent table to make those foreign keys consistent again. Of course, rebuilding indexes is absolute must. And if you have corrupted sequences, they can be only dropped and recreated. There is no other way. And we cannot be sure about their values, so we must set last value based on current data in that table, what is available in those primary keys. So what would help us to make those repairs of corrupted databases easier? Yeah, well, checksums would be the best, but absolute majority of all databases does not use checksums. We would really need some sanity checks in the code to prevent those segmentation fault crashes. This sounds, like Middle Ages. Like I read some bad data, oh, let's try to use them and let's crash on them because, users will understand it. Yeah, well, it's crazy. And as I said, for normal run, those checks could have like really bad performance impact. But when you have really customer, in great shock and you try to repair data, then having this and having possibility to skip those pages, which actually creates those segmentation fault, or tell you, oh, there is some great transaction ID, like, I don't know, some huge numbers, and I am not sure what is the status of that transaction. Yeah, some transaction IDs are ridiculous by definition. Why we take them seriously, So we shall be able to skip, for the sake of repairs, these absolutely ridiculous transaction IDs, or messages like, there is parallel commit not committed, or there is multi-transaction ID not created yet, apparent wrap around. No, this is apparent corruption, and we need to skip it for the sake of repairs. And using this sort of, emergency mode, we would be able to dump data which are healthy enough. We cannot say that those data which we will dump are absolutely 100% clean, but they look healthy enough to be dumped. Without checksums, this is all we can say. We can say that page looks sane enough, or data look reasonably enough for us to use them. So this is like another testimony to using checksums. But as I mentioned in one of those slides, if you would want to add checksums to existing database, it means downtime, and it means also data checks, because it can create checksums of already damaged data, which, yeah, in some situations could be useful, in others not. So this is all what I wanted to show you. And if you have some questions or comments or whatever, please, now is your time.
Thanks, Josef. And we have two questions. First, I'm going to give the microphone to Vic here.
Hi. Why don't we test for tuples too large and offsets too large before, instead of just segfaulting?
Yeah, well, as I said, Postgres is remarkably stable on Linux, and since it existed originally only on Linux, and people avoid, even porting it to Windows, I guess it was, in those days, was not necessary. But later, when we run now a lot of applications on Windows, there is software depending on Postgres running on Windows, like DaVinci video editor or some accounting software and so on. Or on Kubernetes, we are now encountering situations which were not happening before so often. So this is why I want to raise that flag, that these checks would be really nice to have, at least like switchable on off. At least this is how I understand it, and I hope that some contributor will actually say more about it, because I am unfortunately not core contributor, so I just analyze code and try to find what could be improved. Yeah.
Thanks. So there is another question here.
Thank you for a nice talk. A question about checksums, Postgres checksums on a checksum file system. Does that make any sense? Especially if it's going to be turned on by default now. If you run on a checksum file system, should you turn it off because it doesn't add anything, or is there still value in keeping them on when you upgrade to Postgres 18?
I only look at that problem from the perspective of Postgres. I don't have enough knowledge to answer this, I'm sorry. But I highly recommend to use checksums in database, because it's like that first level of defense where you can actually immediately see if something is wrong or not. Yeah, so sorry.
Okay, thank you very much. So despite all those ridiculous transactions IDs and ridiculous blog pages that were corrupted, your content was definitely not ridiculous at all. So that's why we want to give you this nice key ring for you to show our appreciation. So thank you, Josef.
Thank you.